Yeah, we can start with. So, in the previous class, we introduced the 2D element, that is constant strain triangle, and we discussed with plane stress, plane strain concept. So, all 2D elements, whether it's a triangle, quadrilateral, square, rectangle, all these 2D elements can have plane stress condition, plane strain condition, axisymmetric condition. Coming to our syllabus, we have a plane stress, plane strain, axisymmetry of triangle element, and plane stress, plane strain of quadrilateral element. So we introduced the three noded triangle element, which we called constant strain triangle. I just go through the review of the same because we started formulation of the stiffness matrix. So in addition to that, we should see the loading, whether it is going to be a concentrated load in the plane of geometry, or you might have a traction loads. Traction loads acts over a surface. So when you consider in 2D elements over a surface is nothing but if thickness is taken out, the surface area becomes thickness into the length of the side of the member. Similarly, you have a body forces which acts the force per unit volume. So here only area exists, thickness will be normal to the geometry, so thickness is constant. So therefore the body force is per unit area instead of per unit volume, because T we can taken out. So these forces, when they act on a structure, how do we formulate stiffness into displacement equal to the kind of forces? So force summation may be due to concentrated forces, due to body forces, due to traction forces, or thermal loads. So we'll look into those. So what we can learn from this topic, we have understood some of the basics of two-dimensional problems and the concept of constant strain triangle. And further, we'll see the traction force, then body force, the stiffness matrix, and some of the problems we can solve. And we can also introduce isoparametric formulation. What is isoparametric? In general, we have subparametric, superparametric, then you have isoparametric. So we'll see what is those parametric representations. When you look here, the extension of the formulation. So this is some kind of a revision for you. When you take any 2D geometry, when you subdivide, consider an element, the displacement function, what you'll have u bar, what we can write written here u thick, because bar writing is difficult. So the left side, what you have u is because it's a two-dimensional, you have translations in x direction, that is u, and translations in y direction, that is v. Because we are written a row matrix, it's actually a column, that's why transpose. So u and v are the x and y component displacements in a plane of geometry. Suppose if you write the strains induced in the member, your stress vector, when you write sigma x, sigma y, tau xy are three components. Similarly, strains epsilon x, epsilon y, gamma xy. And when you look into the forces, so this F is body force per unit volume. You can have a direction of force in x direction Fx and y direction Fy. These are the body forces per unit volume. Similarly, you have a traction force, the traction x direction Tx, traction y direction Ty. And here the volume becomes thickness into the area. Here also volume becomes thickness into area. Again, when you consider the traction force, it is an area, that becomes dA is thickness into dl. That transformation you have to do so. The T is the thickness in the third dimension, that is z direction. Now, you can see here geometry on the right side with concentrated force at a particular ith point. You have a Px, Py is the concentrated force acting at ith point or ith node. This is going to be a domain, that is the area. You have a traction load of varying or uniform is acting on the geometry. So this is a domain continuity. A loop is given L. Anywhere if you see the geometry, you have X and Y. These your global coordinates. And you have the same xy, if you discretize, then x1, y1, x2, y2, x3, y3, those are all nodal coordinates. Then you have a displacement function vector in x direction u, y direction v. All geometry, global coordinates are x and y. And somewhere you can give some constraints like u equal to 0, v equal to 0, like you can specify anywhere. Then fx, fy are the body forces. Anywhere in the geometry it can act. When typically such a load is acting on the body, then you have a strains induced in the member, epsilon x dou u by dou x, epsilon y dou u by dou y, gamma xy dou u by dou y plus dou v by dou x. This is v, dou v by dou x. And when you write stress-strain relationship, stress equal to on material matrix D into strain. This material matrix for plane stress we have derived in the previous class. Any domain can be divided into small such 2D elements. When we have seen the constant strain triangle in the previous class, you can see the shape functions, how they are varying. When N1 is 1 at node 1, 0 on the edge 2, 3. N2 is 1 at node 2, 0 at on 1, 3 edge. Similarly, N3 is 1 at node 3, 0 and 1 to edge. When you take 1 there, then you can collapse to on the edge. Then how this shape function is varying, you can see how this shape function is varying from that particular node to other edge, and this particular node to other edge. If you superimpose all, then you would find the variation of the shape functions that in turn will give you the displacement variation within the element, strain variation within the element, stress variation within the element, because that is written in terms of shape functions and corresponding nodal values. We have seen that when you have a triangle element, there are 3 shape functions, such we mentioned like N1, N2, N3. So if you add all the shape functions of an element is equal to 1, and you know N1 is 1 at node 1, 0 at 2, 3, N2 is 1 at node 2, 0 at 1, 2, N3 is 1 at node 3, 0 at 1, 2. And if you want to simplify, because this is a 2-dimensional, in a 2-dimensional format, we can use the natural coordinates like xi and eta. So xi in x direction, eta in y direction. When these 3 shape functions, now we can write as in the form of xi, n1 is xi, n2 is eta. When you substitute in this equation, n3 becomes 1 minus xi minus eta. So we can represent the element in terms of global coordinates xy, local coordinates x1, y1, and natural coordinates xi eta. So tomorrow, any element can be expressed in terms of xi eta. Typically, this element, if you can divide into 3 parts by joining corner nodes to a centroid node. Centroid node, you can have imaginary 4th node here, then 1, 4, 2, 4, 3, 4. Then how this xi is varying across. So xi is 1 at node 1, 0 and 2, 3 edge. It's like it's n1. And similarly, here xi is 1 at node 2 and 0 other. Same way we can write n1, eta is 1 here, 0 other. So this we can express it in terms of xi eta also. And when you write these shape functions, we can write in area coordinates also. So simply in terms of area, n1 is a1 by a, n2 is a2 by a, n3 is a3 by a. Or in other words, xi is a1 by a, or xi1 is a1 by a, and eta is a2 by a. Then here, this n3 is 1 minus a minus eta. Even same way we can write in terms of xi eta. So once we know their shape functions, then you can write, and you have a force, loads, whether it's a constant force, traction, or body force. You can write, if you look for energy approach, total potential energy in the system is nothing but strain energy minus work potential. So epsilon transpose into the sigma TdA, because TdA is dV. So thickness is constant, taken out everywhere. So you have area integral written there. So this is strain energy of area integral epsilon transpose d epsilon is sigma. So R epsilon transpose d sigma d epsilon T into dA is the strain energy minus the force. Here what we called is body force. The body force is acting over a volume. So here volume is split into thickness into area. So thickness is taken out. So now the force into thickness into area into displacement transpose is work done by body force. Here work done by you have a traction force. Here traction is over area. Again on the edge we have a dl and thickness is taken out. So displacement transpose into your load is work done by the traction force. This is constant force. So wherever your force are acting in a given body at number of points, you can have summation of displacement into force is the work done. And here we consider it in a 8 point. The loads are two components px and pxy. So because column matrix given transpose. And same we can write in the total energy. Those then you can find out the summation for all the discretization of elements. You can sum up total, then differentiate this total energy with respect to displacement. Then you would find that stiffness into displacement equal to force. And here, if you want find element stiffness, this energy term we can split now. Here your epsilon is BQ and epsilon transpose is Q transpose B transpose. That's what substituted here. Then you can have area integral over dA is A, because here this triangle element throughout is constant, as you know, so no variation. So A over dA is A. Then you have energy is half of Q transpose, thickness of the area is a volume, B transpose dB Q. So then you have a Q transpose Q. If you take out your stiffness matrix is thickness into area of the element E for element, B transpose dB is your element stiffness. And similarly, if you write the same in a stiffness into displacement form, your global, here these are local displacements. When you sum up, you will get a global displacements. So half of Q transpose K into Q. Q is the global vector, small q is the nodal vector. Same way, you can have the body force. So U transpose F into T dA. F you have a components Fx, Fy. U is, UV. So if you write U transpose is row matrix UV and F is a column matrix Fx, Fy. If you multiply these two matrices, U into Fx plus V into Fy. So if you expand that, U into Fx plus V into Fy dA. Again, U you can write N into Q. So U is NQ. N is again N1, 0, N2, 0, N3, 0. And you have the V term 0, N1, 0, N2, 0, N3 is the N matrix. You have components of Fx, Fy. So when you multiply those U and V, if you substitute, then expand, you can write in terms of Q's. Q1 into thickness taken out, dA is right written here inside, N1 dA, thickness is outside, integral, and you have N1 dA, Q2, here Fx force, here Fy force, similarly Q3, Q1, Q3, Q5, Fx components, Q2, Q4, Q6, Y components. So you can have the horizontal components and vertical body forces. And here this integral is area integral. So area integral N1 dA, we can use numerical integration. If you see the numerical integration, I wanted to show you. Yeah. So if you see the numerical integration here, the line integral N1 to the power A, N to the power B, or Xi1 to the power A, Xi to the power B. Any form you can write. Line integral of dl is A factorial, B factorial by A plus B plus 1 factorial into L. Similarly, area integral, when you see N1 to the power A, N to the power B, N to the power C over dA is A factorial, B factorial, the coefficients factorial individually divided by A plus B plus C plus 2 factorial into 2A. Same if you go for 3D elements, volume integral, 4 shape functions, power A, B, C, D over a volume is A factorial, B factorial, C and D factorial. 6 times volume divided by A plus B plus 3 factorial. The same we can use here whenever you have a terms of the individual area integral N1 dA. So N1 to the power 1. So what you get here? 1 factorial into 2A divided by 1 plus 2 factorial. So what do you have? 2a by, here you have 6. So a by 3. This is a by 3, this is a by 3, this is a by 3, this is a by 3. All are a by 3. So that's what given here. It's 1/3 of area. So same way n2, n3 you can do so. Then you can find out all the coefficients. Then area integral U transpose F into dA is Q transpose into equivalent load. That equivalent load is nothing but thickness into area is a volume by 3. The components Fx, Fy at node 1, Fx, Fy at node 2, Fx, Fy at node 3. Transpose of that load. So similarly, we can go for the equivalent load matrix, and you can consider the traction force. Here is an element shown with a traction load. So what you can have when you have a traction load, traction is going to act across the length normal to it. So when it is acting normal to it, and the dA becomes, the thickness is constant, you can take perpendicular to this edge, that surface area you have to take. So perpendicular to that thickness, and the length is a variable. So this is a dl into thickness is the dA for surface area. And that pressure what is acting on this edge can be resolved into two components, one in x direction, other in y direction. So how this variable load is acting even when you resolve into x and y component shown here. So the same we can express here. Then line integral, this is across length, line integral, displacement vector transpose into the traction load across this length into thickness into dl. dl is this length, so L12. This is the variation. Now you can write here ui is uv, right? And t is tx ty. Then when you multiply u into 2x plus v into ty. So when you expand this, u transfer t to dl, u into 2x plus v into ty, thickness into the length. Now u, whatever you have written here, u is n1 q1 plus n2 q2. What is v? n1 q2 plus n2 q4, because v is vertical, u is horizontal. So here displacement horizontal is q1, here is q3. So u is n1 q1 plus n2 q3. Similarly, vertical direction, v is here n1 and q2 is a displacement. And here n2 is a shape function and q4 is a displacement. The same. Same way tx ty you can write tx at node 1, n1 tx1 plus n2 tx2. ty, what is across the length? n1 ty1 plus n2 ty2. So this you can write in above matrix, then expand, then integrate. So once you integrate, you will get the solution. And suppose if you take some problem like a triangle element, coordinates node 1 1.52, node 2 7 3.5, node 3 4 7. And at point P, the coordinates given is 3.85 and 4.8. So when I write this data, you have x1 1.5 and x2 7, x3 is 4. That's what written here. Then y1 2, then y2 3.5, y3 is 7. And given coordinates are xy, so x is 3.85 and y is 4.8. If you use isoparametric representation, that x anywhere is summation of n and x. So here three nodes are there, expanded I equal 1 to 3, ni xi. So n1 x1 plus n2 x2 plus n3 x3. So here coordinates x and y is given. So x and y, whatever you have x and y substituted here, the same thing written here. The x coordinate, y coordinate, then you have corresponding n1 is n2, the n3 is written 1 minus n1, n2, x3. So what happens now? xy, x1, x2, x3 are known, and y, y1, y2, y3 are known. So here unknowns are n1, n2. So two unknowns, two equations you can solve for n1 and n2. So that's what we have done it. So substitution of xy and x1, y1, x2, y2, those coordinates, and you can solve them. Then simplify, n1 is 0.3, n2 is 0.2, therefore n3 is that, then you get 0.5. So if you add n1 into n3, you will become 1. This is a solution for that. Same way, if the same element, if you consider same matrix, find the strain nodal displacement matrix, that capital B. As you know, capital B is 1 by det j. y23, y31, y12, remaining zeros, x32, x13, x21. And these terms reverse, x32, y23, x13, y31, x21, y12. That's what you can see, the third row. Because the first row is sigma x or epsilon x, second row is epsilon y or sigma y, third row corresponding to strain gamma xy or the shear stress tau xy. And 1 by det j is nothing but 2 times area. Now you can substitute those coordinates and the difference of those you can substitute, and you can calculate det j is x13, y23 minus x23, y13. You are getting 28.75. This is twice the area. So 1 by det j you can write, and all the coordinate difference what we have here substituted there. We get B matrix. So then we can have a problem 3, find the strain and stress and the element if displacement vector is given. So Q1 is 0.0 and Q2 is 0.1, Q3 is 0.1, Q4 is 0, Q5 is 0.2, Q6 is 0, Young's modulus is 2 10 to the power 5 megapascal, Poisson's 0.3. So assume that these are mm, so all these mm, so that you can have a consistent units, and you can substitute in B matrix so that epsilon is BQ. You can first substitute epsilon, the B value you can substitute, then multiply with Q's. So when you multiply with Q's, then you can find 1 by 28.75. This, the Q matrix, here supposed to be have to write that Q's values are substituted here. So once you substitute them, then you can have 1 by 28.7 into displacement. You can get strain. Once you get strain, then you can go for stress. Stress is D into epsilon. Now the D, if you consider plane stress. So it's left to you whether you want to consider plane stress, nothing is mentioned. So suppose if you consider plane stress, as you know that Young's modulus by 1 minus Poisson square, nu into Poisson 0, nu 1, 0, 0, 0, 1 minus Poisson's by 2 into strains, epsilon x, epsilon y, gamma xy. The strains you can calculate. So then you can write your D matrix, then you multiply these, you would get the stresses in megapascal. It's going to be consistent units. Okay, numerical integration we have seen. Then the traction force, what we are continuing now. I've given you a traction force which is varying at node 1, P1 magnitude, at node 2, P2 magnitude. Sometimes you can have a UDL load like a P, but here the intensity is changing P1 to P2. In such a case, you know, we have to resolve this components to get Tx1, Tx2 here, and similarly Ty1, Ty2 there. So the length of the member, by knowing the coordinates of 1 and 2, you can find the length of 1, 2 is x2 minus x1 square plus y2 minus y1 under square. If you want to resolve, you need cos theta, we represent C, sin theta, we represent S, cos theta is y2 minus y1 by length, and similarly sin theta is x2 minus x1 by length. Then if you want Tx1, so P1 cos theta, Tx2, P2 cos theta, Ty1, P1 sin theta, Ty2, P2 sin theta. So you can use these sin theta, cos theta on the pressures, then you can get corresponding loads which are acting x direction and y direction. Because whatever normal load, we are resolving to xy components. So these are given here again to explain there. Suppose you want to go for integration, because this is a line integral, n1 square dl. So n1 to the power a dl is, or a length integral, is 2 factorial by 2 plus 1 factorial into length. So 2 factorial by 2 plus 1 is 3 factorial. 2 by 3 factorial is 2 by 6. So 2 by 6 is 1/3. So 1/3 of length. So there's a 1/3 of length. Similarly, you have a terms like n2 square is the same. And if you have right. So if you have again there are multiplications of n1 n2. So length integral n1 n2 is again n1 to the power a, n to the power b is a is 1, b is 1. So 1 factorial into 1 factorial into length by 1 plus 1 plus 1. So that means 1 by 3 factorial or 1 by 6. So you would get 1 by 6 into length. So we get the following equation. Once you expand this Q1, Q2, Q3, Q4, the nodal deformations into equivalent load. So once you substitute all these in the given equation, then you would get the traction equivalent load is thickness into length by 6, 2tx1 plus tx2, 2ty1 plus ty2 at node 1. Similarly, tx1 plus 2x2 and ty1 plus 2y2 at node 2. So this is the equivalent load what we can get. Based on this, suppose if you want to solve a problem. So here a triangle element is given. The nodal coordinates here is a 120, 20 here, and 100, 30, and 50, 60. So 7, 8, 9 are the nodes. When you look this element edge separate, so you have 7, 8 on this element, 8, 9 that element. So first you calculate 7, 8, then 8, 9. So 8, 8 you get belongs to the first edge and belongs to second edge. You can sum up these two components which you get from here and there. So here P1 is 2 megapascal, P2 is 4 megapascal. The same thing if you see P1 is 2 and P2 is 3, X1 is 120, Y1 here 20, and here X2 is 100, Y2 is 30, and we are considering the first edge. Right, so length you can calculate, and cos theta, sin theta you can find out, the coordinates are known. Then Tx1 you can substitute in the equation P1C, Ty1 P1S, Tx2 P2C, Ty2 P2S. So you can substitute these here and you can get. Then T1, that equivalent load 7, 8. You would get this equation, and these components you can substitute there. Then you will get this force, because this is a column matrix we are given transpose. So those forces which we represent F13, F14, F15, F16, X and Y direction. Same way, then you can consider 8, 9 edge. 8, 9 edge, P1 is 3 and P2 is 4. So P1 you can take here and P2 take there. Then X1 is 100 and Y1 is 30, X2 is 50 and Y2 is 60. Then C and S you can calculate Tx1, Ty1, Tx2, Ty2, substitute in the equation. Then you can get the equivalent load of your traction force there. Then you can get all the 4 components. These 4 components, previous 4 components, these 2, and previously these 2, you have to sum up because that belongs to 8. So 8 you have to algebraic sum. Then resultant load vector is this. So this is a way you can solve the problems, whether it's a UDL load, traction force, or anything. Similarly, we can have a CST element subjected to a body force. So your body force is given, Fx is x square Newton per meter cube, and determine the load vector of equivalent. Take element thickness, normal to it is 1 meter. So one you can take. Then body force vector is F tran, you can write U transpose F dV. So U is NQ, so you can write depending on, because it's going to be N1, N2, N3, you can expand. The U is N1, Q1, N2, Q3, N3, Q5. Similarly, N1, Q2, N2, Q4, and N3, Q6. So you can have Q1, Q2, Q3, Q4, Q5, Q6. It will be equivalent load. So then integral here, thickness outside, area integral N transpose dV. You will get it. If you substitute, replace in place of N xi, you can do so. And N2 you can substitute eta. N3 you can substitute 1 minus m minus eta. This is going to be your volume integral. When you write in terms of global x, is nothing but xi x1 plus eta x2 and 1 minus m minus eta x3. So you can substitute x1, x2, x3 values, and correspondingly you can get by substitution of fx is x square. Then you can expand your integral. Then limits 0 to 1, and the second one is 0 to 1 minus xi. Then you can expand this integration, and you know the xi integral power 3, xi integral power 2, or xi integral 1. You can use corresponding integration values previously what we have written and substitute those. After expansion, you get the equivalent volume load. What is isoparametry? So the isoparametry of an element is nothing but there are 2 kinds of displacement functions. One is geometric displacement function. The other one is displacement shape function. If the order of geometric shape function is equal to the order of displacement shape function. Then it is called isoparametric element. Iso means same. So the displacement shape function order, geometric shape function order, both are equal. Then it is called isoparametric. In such a case, when you write displacement UV in terms of zeta or n1, n2, n3, xy in terms of zeta n1, n2, n3, you can expand equally. So if you see U is written summation n1 q1 n2 plus n2 q3 plus n3 q4. Similarly, V is n1 q2 n2 q4 n3 q6. And if you replace U by n1 equal to xi, n2 equal to eta, n3 is 1 minus eta in this, then you can substitute U q1 minus q5, it's wrong, q1 minus q5 into xi plus q3 minus q5 into eta plus q5 after simplification. Similarly, V is q2 minus q6 into xi plus q4 minus q6 into eta plus q6. When you write your shape function matrix, U n1 0, n2 0, n3 0. This n1 is u1, or you can say q1, and this is for y direction 0. Again, x direction 0, x direction, y direction 0. Similarly, b term y. So y terms are exist, x terms are 0. This is your shape function matrix for CST element. The same way we can expand even global xy coordinates in terms of local nodal coordinates. So x is the summation ni xi, n1 x1 plus n2 x2 plus n3 x3. Similarly, y is n1 y1 plus n2 y2 plus n3 y3. And if you substitute n1 is xi, n2 is eta, n3 is 1 minus eta. Same way n1 is xi, n2 is eta, n3 is 1 minus xi minus eta. Suppose if you substitute and simplify, x is x1 minus x3 xi plus x2 minus x3 into eta plus x3. Y is y1 minus y3 xi plus y2 minus y3 eta plus y3. If you give a notation xi is xi minus xj, yi is yi minus yj, then this can be written x13 xi, and this can be x23 eta, then x3. Simplification point of view. Y, y13 xi, and y23 eta, then you have y3. So here observe that u and v and x and y are in terms of xi. That's why we have gone for the chain rule of partial differentiation. There is another concept called convergency. What is convergency? Normally, the convergency is nothing but convergency is general is your solution when you use a finite element, how best it is going to be satisfied so that you will get accurate solution. So from that point of view, this convergency requirements will be used. So I'll discuss these, I think, tomorrow, because we have a time around 1 minute 13 seconds because it's a 1 hour class. All right. So I just stop you, but if you have any questions, I'll share this. You can practice by tomorrow. So tomorrow we'll start our class by 10:10 or 10:15. Then we can we have 2D elements some understanding. So you need to practice these because unless if I write a board, you have a time to digest. It's easy, but when you are expressing here, it could be somewhat difficult. So just think about it and practice, then come back tomorrow. So any questions or any doubt so far, whatever you have?